This video is going to continue to look at the graph of our sine function, and now we want to look at what happens if we start adding numbers to this y equals sine of x, or multiplying it. For example, here we have y equals a sine of bx minus c plus d. A, b, c, and d here are representing our numbers that were either being multiplied or added or subtracted to our function, and we want to explore what effect or what is going to happen to the graph as we multiply by a, or we have this inside of the function bx minus c, and what happens if we add or subtract something on the outside of the function. Well, if we quickly recall, if we had y equals x squared, which we know looks like a u-shaped or a parabola, and if we were to look at y equals a negative x squared, if we recall, remember the negative sign, that causes a reflection, and therefore the parabola would open down. Okay, the negative here in the front. So we're going to see what's going to happen if we do that with our sine function. And if you recall, if we have x squared, let's say plus 4, adding the 4 on the outside, remember that is a vertical shift, so that's going to move the graph up 4 units, whereas if it was a minus 4, it would move it down 4 units. And then we could look at what happens if we add something to the inside of the function. So in other words, we're going to add to 3, then square the function. Recall that causes the graph to go 3 units to the left, and that's where I kind of mentally think of setting x plus 3 equal to 0, and if we solve for x, we get x equals a negative 3. Therefore, the graph is moved 3 units to the left. So that's some of the things we're going to look at here, but we're going to apply this to our sine function. So if you can remember those transformations, they're going to be very similar here. So if we simply look at y equals a negative sine x, this negative in front, what effect is that going to have on our graph? So if I go to our sine function here, I'm going to type in negative x. And again, make sure you use the negative key, not the subtraction key. And notice the graph now, if we kind of focus on the origin, what's happening with the graph. So let me copy this over so we can compare this. If we compare this to the plane sine x here above, we will notice that up here, when we start at the origin, our graph is going up, down, and back up here. But with the negative, notice we start at the origin still, but now the graph is starting out going down, curves up, and back around. So what's happening is we're actually getting the reflection here of this graph. So the negative is going to have the same effect. Now also, you'll notice this a value is actually going to be the amplitude. So the amplitude is going to be the absolute value of a. So in this case, this negative sign is really understood to be a negative 1. So if we were to take the absolute value of a negative 1, then we know the amplitude of this particular graph is 1. And we can certainly see that the amplitude here, if we go from this point to this point, or from this point to this point, it certainly is, the amplitude is 1. And the other part that we want to look at is, I want to go ahead and talk about the period. And the way that we can calculate the period is you're simply going to take 2 pi divided by b. And b is the coefficient up here, sine of bx minus c. b is the coefficient of this x. Well, once again, if we look at our y equals negative sine x, there's nothing in front of the x, so once again that's understood to be a 1. So the period would be 2 pi divided by 1, which is 2 pi. And here we can see that if we start at 0 and it doesn't repeat until here, so this negative has no effect on the period because we still have a period of 2 pi. And that's the same thing that we had up here. So the negative has no effect on the amplitude or the period because the original graph of sine x had a amplitude of 1 and also had a period of 2 pi. So really all that's changed is the reflection. So instead of starting here at the origin and going up, it starts and goes down. All right, the next graph we have, let's look at what if we have y equals 2 sine of x. So if we go to the calculator, we get y equals, we can type in 2 sine of x, and we can look at the graph. And now we can tell this looks a little bit different. And I'll actually on the calculator here, we can actually graph this, but I don't want to really, let me see. Let's copy this over first. If we have the graph here, you probably can see what effect the 2 had. If you notice here from this, we can see that our peaks and valleys are going a little bit higher than before. And even with your calculator, you can, this is something you want to maybe experiment with. If you go to y equals, you can certainly scroll down to y2 here, and we could just type in sine of x, and this way we can look at both the graphs at the same time, and we can see from here that the graph of sine of x is lower. So notice the 2 has actually made the graph go up higher to a higher peak and then down to a lower valley. So that sounds like that is affecting the amplitude. It's going up higher and down lower. So if we look at this, again, we're going from 0 to 2 pi. And the reason I know we're going from 0 to 2 pi because remember, we went to zoom 7, which is zoom trig. So therefore, we know we're going from negative 2 pi to a positive 2 pi. So now each one of these marks going up, again, we know this y-axis is negative 4 to a positive 4. So if we go through looking at our procedure from above, if we want to calculate the amplitude, okay, the amplitude was going to be equal to the absolute value of a. So remember, this is our a sine of x. So we're taking the absolute value of 2, which is 2, and we can see here that from this point to this point, we're going up a distance of 2. So the amplitude certainly is 2. And then if we want to calculate the period, we said that was going to be 2 pi over b, and our b value is a 1, so 2 pi over 1 is still equal to 2 pi. And we can tell from the graph that this graph is still going a distance of 2 pi before it starts to repeat. So here's the beginning of a period, and here would be the end of one period. All right, next, let's look at what happens if we have y equals the sine of x. And I'll put this in parentheses to emphasize this here. Sine of x plus 2. So the 2 here is on the outside. If we go to y equals, we're going to simply type in the sine of x plus 2. And I'm going to leave the other just plain sine function in here, and we can kind of compare this a little bit. So then if we look at the graph, this is the sine of x plus 2 being graphed first, and then second is the original sine function. So we can see here that our function has simply moved up. And if we count here, it looks like it's moved up 2 units. Okay, and that's exactly what has happened here. So if we compare this, and one thing you notice, if you go to y equals, the equal signs here are highlighted. If you go down and highlight the equal sign and you hit enter, notice that unhighlights the equal sign. So now if I hit graph, it's only going to graph the function that is highlighted. So therefore, if I copy this over, we can certainly see the effect that the plus 2 had. So here it looks like everything has moved up 2 units. based on the plus 2. Well, let's go and compare what is the amplitude. Well, the amplitude here, again, this is understood to be 1, so the absolute value of 1 equals 1. And now we can kind of think of right through here is our new axis, so to speak, where the graph, because the x-axis you can think is being moved up here 2 units. So here now we're oscillating the graph up and down below this axis here where we have at y equals 2. So if we're trying to look at calculating the period, once again that would be the coefficient of your x, that's the b value. So that's 2 pi over b, or 2 pi over 1, which again we get 2 pi. So adding this 2 has no effect on the period. So we still start here, the graph still goes up, down, and it ends at this same location. So we still have a period of 2 pi and an amplitude here of 1. So the distance from, again, your axis up to this highest point, this is a period of 1. The only thing that's happened here with the plus 2, the plus 2 has caused the graph to go up 2 units. Now, what do you think would happen? And we'll just kind of experiment with this. If I went to y equals, what's going to happen if I put a negative in front of the sine x with the plus 2? Okay, maybe you had an idea to think about what's going to happen. Let's see if your thought was correct. Notice now, again, it gives us the reflection. So now what's happening by putting the negative in front, at the origin here, instead of the graph starting and going up, it now starts and it goes down. Okay, so here the plus 2 on the outside of the function is moving the graph simply up and down. So now the next graph that we want to look at is y equals the sine of 2x, and notice now the 2 is on the inside of the parentheses, so we want to see what effect that's going to have on the graph. So if we go to our calculator here, we can type in the sine of 2x, and we want to make sure the 2x is inside of the parentheses. So if we go to the graph, and we probably can actually start to notice here compared to the other, we have it looks like a few more peaks and valleys than before. So let's copy this over and see how we can compare it to the sine function. And let's see, let me go ahead and get a copy of sine of x. Yeah, because here we don't have as many peaks and valleys as we did before. And as you experiment with this at home, you can certainly graph both of these again on the calculator and kind of compare. But I want to keep them separate so I can kind of label some stuff here for you. Once again, we're going from 0 to 2 pi here. And again, this graph is from 0 to 2 pi. But we're going to notice something that happens here. From 0 to 2 pi, if our graph starts, it goes up and down and ends here, that's one period. But it looks like from here, up, down, and then to here, this is representing one period. So let's go through and calculate here. If we go to the amplitude, that's the absolute value here of this A value. So that's a 1. So absolute value of 1 is 1. So again here we can notice the period. So from here to the axis, the amplitude here is 1. This amplitude has not changed. So if we calculate the period, that's where we take the coefficient. This is understood to be bx. Okay, we take the b value, 2 pi divided by b. In this case, it's 2 pi divided by 2, and we get an answer of pi. So here, our period has been cut in half. Instead of the period of 2 pi, our period now is equal to pi. So if we start from 0, then that means from 0 to this point here, we have a period of 1 pi. So if we notice then, as we go from here to here, this is representing one period, and then we actually have another period. So this is actually showing two periods as we go from 0 to 2 pi. So this multiplying by 2 has an effect on the period of your function on the graph. All right, so let's look at another example here. So what happens if we take y equals the sine of, instead of 2x, what happens if we make it 1/2 x? Okay, so think about what the 2 did. Now we can kind of maybe think about what this 1/2 is going to do. So if we go in here, we can type in the sine of 1/2 x. And if we go to the graph, and we can really see a big difference here. And now it looks like here we're going up. If we go from the far left to the far right, I'm actually going to adjust the screen here a little bit, because here we only get on the positive x-axis, we're only getting one peak. We don't see, so this is only part of the graph, or part of a period. So I'm actually going to go, well, let's go back to the function for a second here. What can we say about the amplitude? Well, again, the amplitude is the absolute value, in this case of 1, this a value, the coefficient of sine, so the absolute value of 1 is equal to 1. And if we want to calculate the period, that's where we take 2 pi divided by b. Well, now the b value here is this coefficient of the x, which is a half. So 2 pi divided by 1/2, that means we're going to take 2 pi, and we can think of 2 pi over 1, multiply by the reciprocal of a half, so that's 2 over 1. So we're going to get a period of 4 pi. So here, the period is going to be twice as long as what it was originally when we had just the plain sine x, because the period was originally 2 pi, and now by the 1/2, it's making the period 4 pi. So what that tells me, when I go to the window, my x max, the 6.15 is representing 2 pi, so I want to type in 4 pi, and of course when I type in 4 pi it's going to give me the decimal here. So if I type in 4 pi, and now we look at the graph, starting at the origin we should trace out one full period. So we can see here this effect of the 1/2 is creating a much larger period. So now clearly here from the graph we can see that, again, we're starting at 0, and then this time we're going all the way over to 4 pi. So that means starting here to here we end up with a period of 4 pi. But notice again the a is still 1, so our amplitude here has remained the same. The only thing that we have changed is the period. All right, so there's a few glances at some of the transformations, and in the next video we will explore a few more transformations with your sine function.